had lunch. So today, as usual, we are going to have two speakers. Our first speaker is Daniel Wang, who is a professor at the astronomy department at University of Massachusetts Amherst. Daniel received his PhD in astronomy from Columbia University. He was then a Hubble postdoctoral fellow at the University of Colorado and later a Lindheimer fellow at Northwestern. He was also the member of the IAS at Princeton and a Raymond and Beverly Sackler Distinguished Visitor Astronomer at the University of Cambridge. As many of you know, Daniel's main research is focused on high-energy astrophysics, and he's recognized for his pioneering work on the X-ray mapping and spectroscopy of diffuse hot plasma in and around galaxies. And he's also the leader of several major surveys of the Milky Way Center. And he was the principal investigator of several or large number of national and international research projects, which include Hubble Space Telescope, Chandra X-ray Observatory, and XM Newton X-ray Observatory. His current research focuses on the feedback and ecosystem of galaxies and galactic nuclear regions. He mostly uses radio, infrared, UV, and X-ray observations to conduct these studies. He also uses theoretical and computational studies, and he involves a large number of students and collaborators in his studies. So today he's going to tell us about this area and this topic, and he will tell us about X-ray and galactic feedback in nearby disk galaxies. Daniel.
Thank you for coming. Actually, I got the impression, normally the seminars at CFA is not well attended, but thank you for coming. So changed my impression. So anyway, what I want to talk about is something related to the galaxies. Actually, whole idea came from last Chandra meeting. Remember, I gave a short talk on behalf of the panel to talk about what are the future Chandra projects for the Chandra. So one of the ideas I had is about a survey of nearby galaxies. And somebody in the audience here so got interested in to check how many of the galaxies which covered by the so-called Kingfish survey, which is a Herschel infrared survey of nearby galaxies. And to find most of these galaxies have already been observed by Chandra and XM Newton. So why not we get started to work on that? And I have one student who is now in the audience, is going to come over during the summer for the internship here. And so start to look at some galaxies. But today, it's really I want to really put the project in the context, the science context. So why I think it's important to study the galaxies, nearby galaxies in X-ray and in context of big science, I call it galactic feedback. So galactic feedback, by the galactic feedback means in the disk galaxies is due to supernova explosions, both the cold collapse supernovae from massive stars and the type 1a supernovae from low mass stars. And of course, supernovae produce shock waves in the interstellar medium, heats the gas to millions of tens of a million degrees. Naturally, X-ray will be a good tracer for such feedback. And the feedback, in theory, is I think, the weakest link in our understanding how galaxies form and evolve. Okay, so Chandra really can make a huge contribution potentially to this field of gas formation and evolution. Okay, so of course, we already know quite a bit about the X-ray emissions. I'm mostly concentrating on diffuse X-ray emissions, which tracing this million degrees of Kelvin or whatever, the gas in and around the galaxies. So surveys have been done. For example, this is a survey done by my former student, now is a postdoc at Michigan. And you see diffuse emission is ubiquitous. around galaxies, whether it's nuclear starburst galaxies or more kind of disk-wide star-forming galaxies or more crescent galaxies like this one. Now, depending on the also mass of the galaxies, this is Sombrero galaxies and the galaxies which in the Vogel galaxies, which you see ram pressure compressed kind of morphologies as well. So we're here. This sample is like a sorry about that. Like about 53 galaxies, which a few years ago is all nearby age-young, kind of high-inclined galaxies, which is good for studying the gas outside the disk of galaxies. Basically, this is a feedback. We understand how the gas flowing out from star-forming whatever or massive galaxies and influence the called ecosystem of the galaxies. Okay. But what else we can learn? Then we can do statistical studies. For example, here, the luminosity of this diffuse gas X-ray emission versus total X-ray, total energy input from collapsed supernovae plus 1A supernovae. So you see a very nice correlation between these two parameters, which indicates, of course, this is due to feedback very clearly. But over the quite a few orders of magnitude, here in the energy and kind of linear, so when the linear fit, when is a non-linear fit, but more or less you see very nice correlation, okay? But this is one surprise actually in my mind is this X-ray emission is a very small portion of the energy input into the interstellar medium. It's like a 1%.
How is the energy from the supernovae determined?
Is basically you can trace either the infrared, far infrared traces the star formation rate, that you know how many explosions for collapsed supernova explosions, and you use the, let's say, K-band to trace all the stars. It gave you a very good handle on the rate of type 1A supernovae. Okay, then you assuming 10 to 51 ergs mechanical energy input, then get the total amount of energy input. Okay, kind of straightforward, but within uncertainty probably effect of 2 also. Okay, it's not orders of magnitude. So the point here is a very small fraction of energy goes to the X-ray. Okay, so what's the problem here? But we expect a supernova explosion producing hot gas, which should be observed by an X-ray. But we don't see it. At least this is a phase age-young galaxy. And then I did just last year also did a little more kind of analysis instead of just look at the correlation between X-ray luminosity and the star formation rate, which is always correlation versus correlation with what that mean. So let's do some specific parameters. Here's a specific. Use the specific X-ray luminosity, the per K-band luminosity, so you kind of become distant independent parameter. And here is also star formation as scaled by the mass. So therefore, this is distant independent also give us more specific correlation. And you find actually the correlation is very sublinear, okay? Which is kind of surprising. I will tell you why. Let's first to look at also this plot here. This is as called X-ray efficiency per star formation rate. Okay, so as function of the surface star formation rate. So basically, surface is in the galaxy determined by the size of star forming disk, which is traced by 22 micron emission, for example, from WISE. So that gives you, say, how the surprisingly, actually, this gets anti-correlation, which is theoretically, actually, you predict that totally should be positive correlation because the X-ray emission is proportional to density squared if you assume this is from brainstorm radiation or line emission, right? So the star formation, if you assume, okay, more star formation means more gas into the hot gas, the density square, then they should be proportional to the star formation rate. But actually, it's anti-correlated. So that is theoretically it's not explained. Okay, that means actually mass loading either if you assume the hot gas here seen in X-ray does trace the energy input. That means mass loading has to be decreased very fast with increasing specific star formation rate. Okay, so that is kind of surprising and not understood. And then look at the temperature versus say kind of effective mean temperature we can do with change like that versus its specific star formation rate, and then find the hardly change. Actually, more or less 2 or 3 times a million degrees. That's what we're talking about. But slightly increase with the specific star formation. It's not a huge increase. Mostly, according to the theory of any super wind or any outflow, you will expect actual temperature to be much, much higher. Will be kilo EVs. Okay, but it's never got to that stage. For what you see in the change of that. Okay, so that is. So my interpretation is not necessarily correct. I think no model, no interpretation is correct anyway. So is actually what we see here in the soft X-ray band, which Chandra is sensitive to, is we're not really seeing the volume filling kind of outflow of real hot gas. We are talking about is mostly is the interaction of the hot gas probably through the charge exchanges, this kind of surface phenomena. Okay. So X-ray is not tracing what we see in soft X-ray, not tracing the volume filling the hot gas, but mostly I think is the interface between hot and cooler gas. And this is to some degree is consistent with the long timing puzzle to me is always see in the starburst galaxies the good correlation between X-ray emission and H alpha emission. Okay, so that because if most of the X-ray soft X-ray emission arises from the interface, that is a natural explanation. So we really have to understand the nature of X-ray emission from a galactic colony, okay, whatever we talk about this diffuse emission around the galaxies. So let's look at the familiar pictures of M82 starburst galaxies. And you see actually nice correlation, actually even some detailed correlation between X-ray emitting gas, which is color coded in blue, with say the dusty or the H alpha emissions in red or in green. And so we want to have a spectroscopic work to really understand the nature of the X-ray emission. So this actually is the XM Newton RGS spectrum of M82. Nice, large lines, familiar lines, mostly helium-like or oxygen-like or hydrogen-like transitions, K transitions, and especially here, let's look at this helium-like or oxygen-7 lines in details. You see actually forbidden line is stronger than the resonance line, which is surprising again. If you assume it's a collisional excitation with a temperature a few million degrees, you expect the the resonance line should be much stronger than forbidden lines. But what you see is different. That tells you this forbidden line is naturally explained by cascading of photons, not collisionally excited, because that's almost by the resonance line means this is electric dipole allowed ones. Forbidden line means high order transitions, which is less probable. So, but if the electron comes down from high energy levels to down levels, it's all depending on the quantum states, number of quantum states. So forbidden line has more quantum states, therefore if you have something like cascading down, either due to recombination or due to charge exchange, which go to the high energy levels going down. So naturally, you expect this kind of non-collisional excited transitions will produce stronger forbidden lines than the resonance lines as you observe. And so actually, see, so that's what we said. So actually, one of the my student here And actually, so try to model with a model developed by the Randall and others. And so let's try the forbidden this charge exchange model with simple toy model. So assuming you have a hot gas flowing out from the disk of the M82, now this is single temperature, and now have a charge exchange with the surface, whatever. Okay? So let's just put these two models, link them together to get a fit. So this is, again, the RGS spectrum. Here is some continuum due to the point-like sources, like X-ray binaries. Doesn't matter because it doesn't contribute much to the line emission. And then you add on a thermal, single temperature thermal plasma contribution. And you explain lifelines, but not some other lines, especially like oxygen lines here. Then you say you join the fit and get a charge exchange contributions. Because charge exchange is just highly ionized ions steal one electrons from neutral atoms, and so you reduce one charge in the ions. So say naturally will contribute mostly the cascading down, produce X-rays. So naturally explain the soft X-ray part. So explain charge exchange component here gives a very nice contribution to this relatively lowly ionized species. So combination of them will be very nice fit, very simple toy model. Okay, just a single temperature plasma to the charge exchange with some surface, and it gives very nice to these complicated models. Okay, so that's the process. So which I think is very reasonable at least. If we, I will not say the correct interpretation, but real life always a little more complicated than that. Okay, so that actually gives a handle. Potentially is through charge exchange observations you can probe what's the interface, how big is the interface, because charge exchange is proportional to basically the ion flux into the cold medium. Okay. There's no other ways to do that. So I think through the study of charge exchange, potentially you can study the interface physics, which has been very, very hard for any simulations or theoretical studies.
Daniel?
Yes?
What if you use the multiple temperature model instead of the charge exchange?
No, you can, of course, add enough components, you can get a better fit, but you cannot really make the forbidden line stronger. Okay, that's real key diagnostics. And yes, you can all have a chi-square reduced, no question about that. But you cannot really look at details, the forbidden line versus resonance lines. That's actually the key, really the key. Actually, not only the M82 shows this kind of strong forbidden versus resonance line, but you see every time we see have a reasonable signal to noise ratio for oxygen lines, you always see the forbidden line strong for star-forming galaxies. So this is the nucleus of M83. This is M51. Basically, is called G ratio. This is the forbidden plus interrecombination line to the resonance lines, always greater than 1. So this is pretty universal. That cannot be explained by simple critical excitated plasma. Okay, the period. Okay, so something new physics has to be added into to understand the nature of soft X-rays. And this is more work, of course, done by others. Now look back to the images. There's some earlier work by, I think these are quite good papers, but didn't have much follow-up work, what we try to do now. This is M83 again, I think. So this shows diffuse X-ray contours, soft X-ray contours on the H-alpha images. And the key point is here, see H-alpha correlates very well with X-ray emission, which to me is kind of surprising. There's no offset. Because the lifetime of the massive stars is something like a few tens of a million years, which as it evolved, when spiral arm, the gas falling into the spiral arm, of course, form stars. The stars then should have moved away over the lifetime away from the spiral arms. But we don't see such offset, at least in such studies. Okay? But more recently, actually, it's a much better paper. So what's the question is, where is the feedback energy from massive stars of few 10 to 7 years? That's the lifetime of the, say, 8 or 10 solar mass stars, which are capable to do the supernova explosions. Okay? So energy input in the alpha arm regions are not seen in the soft X-ray image, at least in the previous studies. But they are now much more sophisticated, much deeper observations. I think you just see actually some signs, even things which is sharp edges of these spiral arms, and there's some extension down in the downstream. But there's no such study yet. So that's basically one of our goals of, I think, survey of nearby galaxies. We want to study especially resolved diffuse emission, especially in the context of R-arm and off-arm, to see the evolution of the hot gas and compared to the evolution of, say, the energy input from massive stars. That's why I think it's pretty interesting. I try to, please comment. I want to solicit your comments and even solicit helps if you are interested in this project. Okay, this is a kind of advertisement. Okay, so the idea is actually it's illustrated here. So you have a spiral arm which triggered by kind of clouding into stars, okay, density wave, of course. Then you have stars moving depending on where you are, depending on the radius. So the center is around here. Then you start forming around here. Okay, this is that's because the density increase, it triggers the star formation. Then stars will start moving downstream to become older and older, but we're moving away from the spiral arm. So keep pumping energy in kind of more or less constant rate, assuming a standard IMF, initial mass function of the massive stars. But now we don't see clear evidence, certainly not uniform. So where is the gas which in the interarm regions? There's some even more recent studies here. I think this is very nice work. And actually, you look at the radio polarized emission in particular, you find actually polarized emission tend to be all the interarm regions. And this is based on the study of XM Newton, that spectroscopic spectral study. You also find the gas in the interarm region tend to be higher than in the arm regions. Okay, I have some theory or scenarios to explain that. But I think it's very encouraging. So this tracer, with modern or deep changeable observations and or whatever, and the radio observation, actually we see this energy there in the interarm regions, which may not seen directly as strong radiation in soft X-ray. Okay, so that's the kind of study we want to do. Okay, and so I put if we have one question, this is the question: where is the feedback energy? What feedback energy is doing to our two galaxies? So scenario one is you can consume all the energy locally in the arm. That's why gives a good correlation between the H alpha emission and the soft X-ray radiation. So, but we don't see that in soft X-ray because I tell you, only a few percent of mechanical energy input from the supernova can be explained by the luminosity of you observe. The second, second scenario is you have outflows, which probably is very ubiquitous, and even in normal galaxies, but it's just energy just mechanically moved away in the kind of wind. Okay. So, but temperature has to be high, density has to be low, mostly probably in the interarm regions. That explains the relatively high temperature of gas in the interarm regions. But we still don't know. We need a large sample of such galaxies to careful studies. I think we need to test such scenarios. So, okay, so what we really want to do is do something like that. Okay, so this is a Kingfish survey of galaxies, about 61 nearby galaxies. We want to produce X-ray images like this, have a poster like that. I think that's a good service for Chandra program. Okay, so this of course they have this the middle infrared, also H alpha observation, all kinds of longer wavelengths observations, and we want to match that with X-ray emissions and combine all the information we have across the spectrum to really understand how the relation between star formation and the diffuse hot gas, how the feedback works in such disk galaxies. Okay, that is so that's a wonderful. My favorite gas is not. So we have focused on the Edge-on galaxies. Few work for the face-on galaxies. I think some intermediate inclined gas will be good. One example here is you see actually the X-ray emissions, diffuse X-ray emissions stands out. This is very massive galaxies can seem to be flowing out. I have no proof of that, but you see it's just the orientation. You see, actually, I think it's very nice. Actually, see extension. So basically, as this kind of galaxy, you can see the link between the extraplanar gas and to the star formation in the disk, which you cannot really appreciate in the complete Edge-on galaxy or in the face-on galaxy. I think that's something we're still missing very much in the current studies. So these are the questions we want to answer. What fraction of the feedback energy can be converted into thermal energy of star-forming regions, and what conditions does the gas can escape from into the halos, and how far the gas can escape into the halo. So this kind of scaling, so extension into the halo will be really tells you what is dynamic state. So of course, they require some modeling without the kinematic information, and how all these depend on the specific star formation and other parameters. Okay, so this is my summary. And so nearby disk galaxies really is an excellent laboratory for us to have multi-wavelength studies of the feedback process. And you see the beautiful simulations, but these all depending on the recipes, and which are not tested well. And the nearby galaxies are the laboratories. You can test these recipes. Okay? So that's the key message. The existing X-ray observations already show some inconsistencies in theory. We actually have papers published. There's no match really between theory and observations. So theory can predict X-ray emissions, which is totally different from what you observe. Physical process like charge exchange and resonance scattering and photoionization, you could put the agents into the game. So we are all playing all these games here, but I will not have time to talk about them. But you should invite Srinath to give a talk here, okay, later. So he'll tell you something details about these processes. And the cosmic ray magnetic field, I think, could potentially be very, very important. Although normally about 10% of energy from the supernovae maybe go to the cosmic rays, but cosmic ray is hard to dissipate energy. So which may have very strong implications for how the feedback works. I think that's something with nice radio data combined with X data, we can see what's the relation between, say, the outflow driven by cosmic rays or by hot gas, which we don't know actually. So actual data are available, even archival. We can start to actually analyze to advanced field. Eventually, of course, we could have some new observations as well. But basically, this is my myself to you. Okay.
Thank you very much, Daniel. Questions?
How many of the galaxies you showed on that big Herschel slide?
61.
And how many of them have been observed by
50, right? We have about 50 are already observed. Yeah. But some are not very deep, very, very shallow. So we first have a look of the data. So that's basically what we want to try to do. We'll have students working in summer here and try to help out the project. Yeah.
different. So does it tell us something about structure that we wouldn't otherwise be able to measure?
I'm not sure exactly what you mean, but so he observed strong correlation between H alpha and the diffuse X-ray emission, soft X-ray emission. Is very striking. Okay, that means one possibility is the soft X-ray really comes from the interface where you have both the H alpha emission and X-ray emission, the like charge exchange event. And the other possibility is basically, you all the energy basically is consumed locally in the very young stubble forming regions. But certainly not in the outflow region. You cannot explain that. Yeah.
Along those lines, you can actually do a pretty straightforward calculation of what the charge exchange contribution to the H alpha could be, just straight from neutral and ionized and protons interacting will give you H alpha from charge exchange. And then you can use that as a baseline for if that's how much charge exchange is going on in H alpha, you can at least tie that to the X-ray, the soft X-ray charge exchange. In most cases, there's lots of other processes, of course, that are going to generate H alpha, but you can at least get an upper limit or a...
Yeah, unfortunately, because we are looking at star burst or star forming regions, so much of the bulk of H alpha emission comes from the combinations from the photoionized, the gas. But this is one thing when people can do is charge exchange, you have broad wings. So you can spectrum, if you high resolution spectrum, and you can actually, like IFU especially, if you can actually basically to measure the H alpha contribution in the high velocity wing, that's is a contribution purely almost from the H alpha, from charge exchange process, which is known, of course, in supernova remnant studies. Okay. Then if you can really, that's of course H alpha actually charge exchange is well known in explaining this kind of high velocity, high dispersion H alpha emissions. I think this is just in retrospect, it's no brainer. Now the question is really you can quantitatively measure, as you said, measure charge exchange H alpha contribution, which I think is super important because which is directly proportional to the surface between interface surface between hot gas and cool gas, which is very much determined by turbulence, which is in theory you cannot really simulate that process. It's super important.
Wonder where we can find one of those.
Yeah. No, of course. I'm a little bit shorter. So looking for
Okay, so our second speaker is Jonathan McDowell, so everybody knows him. I hope it's not that you will know him after this talk. So Jonathan has a long history in astronomy, as you would guess, but it's and his astronomy career started right after high school when he worked for 6 months at the Royal Greenwich Observatory. And I believe that because of this, he was motivated to start his PhD at the Institute of Astronomy at Cambridge, not this Cambridge, but the other Cambridge, where he was working on the theory of submillimeter background radiation. But after the theoretical study, he wanted to move to observations. So first he was working on the microwave background, but then he got interested into the quasars, and I guess he's still interested in quasars. He came to CFA as a postdoc, and then he moved to Huntsville, Alabama, but then he really loved Cambridge, this Cambridge, so he moved back.
Any Cambridge.
Any Cambridge. He just liked Cambridge in general. Okay. So Jonathan is also known from his newsletter, Jonathan's Space Report, which is issued about twice a month, and it describes all space launches, including both piloted missions and automated satellites. And I think his talk today will be related to this, and he's going to tell us all you wanted to know about space junk.
Thank you. Yeah, so happy Cosmonautics Day, everyone. It's April 12th. It's the 56th anniversary of Yuri Gagarin's flight today. So the first satellite, Sputnik, was launched almost 60 years ago. The number of satellites in space has increased a lot since those days. In the early days, there were only a few satellites in space, and famously, space is big, so we had the same attitude to it that we had to the oceans, which is, oh, we can throw all kinds of stuff up there, and it'll never fill up. When we think of the height of the space age, we often think of the 1960s, but only a few satellites were operating at any one time there. They didn't last very long. This is active satellites versus time. It's hard to say because some space agencies don't email me when they switch off a satellite, but this is the best estimate. And today there's over 1,500 active satellites, and the number is rising really fast. Part of that is that in the past few years we've seen an explosion in the number of CubeSats. CubeSats, sort of open standard satellites, typically about 5 kilograms, about yay big. And the first one was launched in 2003, but this shows the launch rate over time, showing that it was really only in 2013 that the miniaturization of components, the development of support services and so on got to the point where it moved from aerospace engineering master's program courses where you put a webcam on your satellite and declare that success, to satellites that can actually do something useful in this small package. And so now we're getting over 100 a year. There are 611 CubeSats launched to date. About almost 300 are probably working at the moment. They're from 38 different countries, mostly from the United States. And most of those, over 260 of those, are from a single company called Planet in San Francisco, which is launching a large Earth imaging constellation. So if you look at the distribution of what's a typical satellite mass, this is a histogram of log satellite mass. And this is, again, just the active, the working satellites, not the space junk yet. We see that between 1 metric ton and 10 metric tons is sort of the typical satellite historically. This is from 1957 to 2009. Nanosats below 10 kilograms in blue here were a small fraction of the satellites launched. But since 2010, that distribution has dramatically changed. So this is the quantitative statement that CubeSats have really become an important factor. But you'll notice that the mode is still in the 1 to 10 ton range. There are still hundreds of satellites being launched of these larger kinds. So the problem is, of course, that every time you launch a satellite, the rocket stage goes into orbit with it. And so if you don't do anything special, you end up with a piece of space junk for every space launch. So at the bottom here in red is the same data that I showed you for the active satellites versus time. These are the active satellites. But then added on are the various layers of different kinds of space junk. And so you'll see that we have dead satellites that stop working are still up there, rocket stages, things that you throw overboard, adapters, and so on. The green is explosion debris of various kinds, and so that's a huge contribution. And then the top two things, you see this big jump around 2007. Just 2 incidents contributed several thousand pieces of catalog space debris. There was a Chinese anti-satellite test in 2007 where they blew up one of their own satellites deliberately in just the worst place, as I'll show you later. The cyan one is 2 communication satellites which smashed into each other and had a bad day in 2009. And I'm going to, if I have time at the end, I'll go into more detail about that particular event. So this shows that for all the effort that I'll describe in a minute that's gone into creating less space junk, it only takes screwing up once or twice to make things very much worse. This is the same data, but in terms of tonnage. So my estimate from my own catalog is that there's almost 9,000 tons of material in Earth orbit right now. And what is it all? you'll be relieved. I'm not going to go through this in detail, but just to give you a sense of the different kinds of space debris that we have, a large part of it is this explosion debris, 10,000 pieces, of which the biggest contribution is from what I call residual fuel explosions. If you launch a rocket, you don't, you always leave a little extra fuel, right, just in case. And so you've got a little extra fuel left over, and if you don't do anything with it, you've got fuel and oxidizer and maybe some gaskets separating them that erodes over time. And at a certain point, like 5 years after launch, suddenly the rocket blows up and creates lots of pieces of debris. So you can fix that by, designing your engine to be restartable so that after you've delivered the satellite, you reignite it, run it to depletion, and that's been going on for a couple decades now, and more recently have enough fuel so that you can actually deorbit the rocket stage entirely and remove it from the space junk population, and that's now reasonably common, but there's still a bunch of these time bombs out there of rockets with leftover propellant that are contributing to the debris population, especially these little strap-on motors that are used on Russian upper stages, that are a bunch of them being jettisoned, and I think about 40 of them have blown up now in relatively high orbit. Anti-satellite weapons tests have the next biggest contribution, and that's easy to stop, just don't do that. And I think we've persuaded the Chinese to stop doing it. The US has done some tests. They've done it in relatively low orbit where the debris re-enters fairly quickly. Still a bad idea. And then accidental collision is only like 1,500 of these. But there's a problem, which is that all these other sources of debris go like the number of satellites. They go like n. And satellite-on-satellite collisions go like n squared. And so as the number of satellites increases, and you saw my plot, it's going up, and it's going up really fast. And so we expect to see more and more collisions. And so this is the famous Kessler syndrome, the chain reaction in Earth orbit that will shred our space program into Saturn's rings made of aluminum. And its doubling time scale is quite a few decades, so it's not a panic situation, but if we carry on ignoring it, it's going to be a problem. Just to mention, among the other little sources, we do have 14 ejected nuclear reactor cores orbiting at about 1,000 kilometers, and that was from the Russian Navy, thank you, Russian naval intelligence who operated their spy satellites using nuclear reactors. So I want to talk about where these objects are. And so you can get a long way with just very simple Kepler's laws. Unfortunately, I can never remember the units of big G, so as an old black hole guy, I use the gravitational radius where the Keplerian velocity is just V over C is square root of RG over R. RG for the Earth is 4 millimeters, so you can, that's the size the Earth would have it for a black hole, so you can very easily then calculate that at the height of the space station, the Keplerian velocity is about 7.7 kilometers a second. And the fact that that's, by terrestrial standards, a fast speed has a lot of energy in collisions. That's the root of why space debris is a problem. Let's just see where it is. So here, this is versus log of height above the Earth, the current satellite population with the operational satellites in green, the dead satellites in red, and the junk, the full-up junk in black. And the distributions are pretty much the same for the three populations. Most stuff in low Earth orbit, LEO, between about 400 kilometers. The ISS is sort of at the bottom end of where the satellite population is, to about 1,500 kilometers. And then two narrow spikes at a 12-hour orbital period where the GPS satellites are, and a 24-hour orbital period where the communication satellites are. So let's just map this in terms of just orbital parameters to start with. So now the y-axis is orbital inclination. So at the bottom we have equatorial going east. At the top we have equatorial going west. And in the middle we have polar orbits. And so what I want you to take out of this is the narrow feature here, which is the active geostationary satellites. There's the GPS. High orbit objects tend to be equatorial. Low orbit objects tend to be polar. The sun synchronous orbit here at 97 degrees, very popular. And then no one launches west because as the Earth turns, you get a free boost from going west. No one except these three little green dots at the top left, which are going the wrong way around the world. So you've got to have a really good reason for launching west and losing all that payload capability. Israel has a good reason, which is if they launch east, they start a war. And so, and so their spy satellites go around the other way to everybody else's. So what I did then, just to kind of quantify how crowded space is a bit better, there are 18,000 satellites currently tracked in Earth orbit. I meant to mention in low Earth orbit, the US radars and cameras are pretty complete down to 10 centimeter size objects. We don't know too much about the population below that. There have been pencil beam surveys for statistical estimates. And then things get much more incomplete as you go up to things like geostationary orbit. So this is a lower limit on the population. So what I did was I took all the satellites at around 800 kilometers or so, ran their positions for every minute for a 45-day period to get sort of an average location. And what we have here is the mean free path. Think of the satellite population of the Earth as a gas. And it's typically a few hundred kilometers, like 300 to 400 kilometers. But you'll notice this blue near the poles where all the sun-synchronous orbits intersect, where it drops by a factor of 2 or so in mean free path, a factor of almost 10 in number density. And so if you're going to get a collision, you're more likely to get a collision near the poles. And that's exactly where the communication satellite collision happened in 2009. This is another representation of the same data, but this time the x-axis is altitude, going up to geostationary orbit here. This is the region we looked at in the previous slide, and this is latitude. And so there are a couple of fun features here. So you can, as I say, you can see geostationary, you can see the GPS, GLONASS, and Galileo navigation constellations. You also see these weird horizontal structures which mark out the latitudes of various launch sites. And so if you launch a constellation into a particular orbital inclination, they never go north of that inclination. And so you essentially get different disks of sort of thick disks, if you like, of different radii and heights surrounding the Earth. And I was trying to think if there's an astrophysical equivalent to this sort of multiple disk population like that, but I don't think there's an exact analog. So just to emphasize how well Kepler's laws work, not that you didn't know, I'm going to go back to the earlier plot of height versus inclination and zoom in to look at the active satellites in geostationary orbit, and you see the semi-major axis of the active geostationary satellites is exactly at the predicted value to within 1 kilometer. There's some eccentricity, but the semi-major axes are really dead on in operational real life. And the red ones up here are retired satellites that have been boosted to higher altitudes, mostly what we call the geograveyard. And they're at higher inclinations because lunisolar perturbations tend to move the orbits away from equatorial once you run out of station-keeping fuel. So Kepler's laws are all very well, but you need to go one step further to have real fun. The first-order perturbation due to the oblateness of the Earth gives you a rotation of the perigee and of the orbital plane. So the ellipse rotates in the plane, and the orbital plane rotates just as we're used to in other astrophysical contexts. But because we're engineering this, not observing it, we can pick orbital parameters to do fun things. First, let's, if you pick this term, 2 minus 5/2 sine squared I, the rotation of the perigee, and you pick I as 63.4 degrees, this term goes to 0, and you can lock the perigee in position. And this is kind of fun for if you have a surveillance satellite in a big elliptical orbit over the northern hemisphere. If you didn't pick the inclination carefully, that orbit would rotate anything up to several degrees a day until the perigee was in the southern hemisphere, where it wasn't the area you wanted to be looking at. So by picking this special value of the inclination, you can lock in the perigee in the northern hemisphere. This is called a Molniya orbit, after the Russian satellites that first used this, so it comes in very handy. Then for the orbital plane rotation term, that's of course how you get the sun-synchronous orbit, which many of you are familiar with, taking the cos-I term that turns the orbital plane to exactly match the rate at which the Earth goes around the Sun, and keeping the Sun-Earth vector to orbit normal vector constant. And so that's fine. We all know that theory. The purple line is the theoretical curve that goes like cos I times semi-major axis to the -7/2. And the green crosses show the actual data of where active sun-synchronous satellites are in this region of parameter space. Yay, they're all clustering around the line. It's not quite as tight as for geostationary. This shows you that, this simple theoretical model is used in real-life practice. And it also shows you all this black space debris stuff. That's the Chinese anti-satellite test. That's why it was so bad. It's right in where you want your sun-synchronous orbit satellites to be. That's the region where it drops to over the poles to a couple hundred kilometers or 150 kilometers, right?
Free separation?
Yeah, I mean mean-free separation is what I mean. N to the -1/3. I'm being sloppy with my terminology. I apologize, Dan. So yeah, it's the n to the -1/3 mean separation, and again that changes where the satellite is in its orbit, right? So that plot was for actual positions, and so the satellite takes 90 minutes to go around the Earth, and every time it goes over the poles, the local number density increases, and so indeed, funny you should mention that, over Siberia in 2009. The Iridium 33 satellite was happily orbiting around, and a dead Soviet communications satellite came at it at a little over a 90-degree angle. And so the relative velocity, this is 776 kilometers above the Arctic, the relative velocity is 11.6 kilometers a second, so that's escape velocity, right? And so that has a kinetic energy of 54,000 megajoules. Of one satellite in the frame of the other, which a megajoule is a great unit for this. It's a 1-ton truck hitting you at 100 miles an hour. And so when you get 54,000 of those in two truck-sized objects, some damage was done. And the top left diagram from Tom Kelso's paper on the subject shows 3 hours after the collision, the debris objects are spreading out along the orbit of the satellite, very much as meteor streams spread out along the orbit of comets. What then happens is, over a period of time, they're at different heights. They get different plane rotation rates due to the oblateness, and so that spreads out first into a shell around the Earth, and then a thicker shell as orbital decay takes over. Some of the objects from 2009 to today, orbital altitude, mean orbital altitude for a few selected pieces from this collision, and a couple of them really haven't changed their orbits much, but some of them have re-entered, and this is sort of the typical decay curve you have. Things don't decay very much at first, and then as they get into the denser lower atmosphere, but even around, this is only 500 kilometers here, you're really starting to see effects, because a lot of the debris pieces have relatively large surface area to mass ratios, and so they come down. They have a lot of drag. They come down quickly compared to your average satellite, and so if a significant fraction of the debris from that collision has now re-entered. As an astronomer, you might normally plot things like orbital period versus eccentricity for the debris population. This is the sort of thing you might do for if you're an asteroid scientist. Rocket people use a thing called the Gabbard diagram, which is mathematically equivalent. You plot separately perigee and apogee versus orbital period. So here's the orbit of the thing that exploded or collided, and the debris populations. Basically, if you have something in a circular orbit and you add energy to it, it's going to end up in an orbit with one end of the ellipse at that same altitude, and the other one either higher or lower, depending on the direction of the thing. So you get this sort of one-parameter sequence, which is very nice. Toward the end here at the left, this is a plot showing the orbits 1 year after the collision, and the lower period objects are starting to get circularized and move down towards reentry due to atmospheric drag. And then today, 10 years or 7 years after that, that left-hand thing has just been completely circularized, and things are the lower orbit ones are moving down to reentry, but the higher orbit objects really haven't changed their orbits very much. And what's kind of fun is, although they've spread out, this is latitude and longitude of just an instant snapshot of where the debris objects are at any given time. They're spread out all over the Earth. They haven't spread out much in the x-axis here is height, and they haven't spread out at all in orbital inclination. So this is right ascension of ascending node on the x-axis, inclination on the y-axis, and you see that 8 years after the collision, the orbital inclinations of the debris objects are still fully separated. So you can immediately tell, oh, this piece of debris was from the strela, this piece of debris was from the iridium, it's quite dramatic that there's no mixing there. So that was a pretty bad collision, and it's sort of the worst case. That we talk about, should we clean up debris by zapping the little pieces with lasers, or should we get tow trucks to take the big debris pieces out? And the whole chain reaction Kessler syndrome thing, people have modeled that it's actually the biggest worry is the big pieces hitting each other exactly like this. That's going to make the debris population, it's going to drive the big increase. So we should, I think, tax satellite operators to run a garbage tax that would fund a fleet of tow truck satellites and get rid of the big junk. That would be my solution. We really worry about geostationary orbit. That's so precious, and as you saw, it's very narrow. So it would be easy to have a lot of debris in that space. But actually, it's not so bad because it's 6 times higher radius, so root 6 slower. And all the objects in geo are going all around the same way. And so their relative velocities are actually quite small. Even a relocating satellite is only going relative about 0.1 kilometers a second relative to the other satellites. The problem is the rocket stages and the exploding rocket stages and their debris, which are in these transfer orbits that go from low near the Earth up to geostationary, hitting geostationary orbit at an angle. So they have relative velocities to the geo things. I did a calculation for a recent SpaceX launch. The payload's now in geostationary. The second stage is junk in elliptical orbit. When they're at the same altitude, their relative velocity is about 1.7 kilometers a second. That's still significant, but it's still almost 50 times less kinetic energy than for the low orbit event. And so really I think the big danger for the space debris issues is in the low orbit and not in geo in that sense. So I think that's it, and I'm running out of time. So that just gives you a sense of the current state of play in satellite debris and the population of the space environment. I'll just put up... all right, let's try this. This one, which I think is fun. And I'm working with the folks at the European Space Agency at ESOC in Darmstadt for sort of improvements to our debris catalog to tag everything in these various different categories and sort of be able to sort of manage better what is the current state of things. So thanks a lot. Hope this was entertaining for you. Question?
So presumably there is some sort of debris mass function, right?
Yes.
What mass can you see it, and how much is there below that mass?
Right. So that's exactly right. And as I said, in low orbit, it's usually expressed in terms of size rather than mass. We can see down to 10 centimeter objects, and actually a little smaller than that. And that's a problem because the smallest satellites now are smaller than that. The what are called pocket cubes. And so we're getting to the point now, and there's even a guy at Harvard, Zach Manchester, who's developing these things called sprites, which are little 5-gram circuit boards that are going to be just really tiny to try and track. So that's a problem. Haystack's done pencil beam surveys to measure the mass function or the size function down to smaller masses. That I haven't seen a recent one, but 10 years ago there was one that sort of estimated that. So we know a little bit about that. There's one of the big contributions at the smaller sizes, I didn't mention, is solid rocket motor slag. That when a solid rocket motor fires, all kinds of stuff comes out the back end. Doesn't burn fully, and that's a significant contribution. In the past, solid rocket motors have gone out of fashion for orbital use. There's very few used now at the orbital level. There are lower stages, yes, but not for orbit insertion. And so that population is decreasing, I think. Another source, there's special sources at different altitudes. These nuclear reactors from the Soviet satellites have been leaking coolant, and they've discovered these nice reflective spheres of sodium-potassium liquid coolant blobs that have a nice radar return. And there's a couple hundred of those in the catalog, I think. Yeah, 53 still in orbit. So there's various other weird things that come in as you go to the low mass range, but there's still a lot of uncertainty down at that point. And the big uncertainty is at the high altitudes at GEO, how the exploded rocket debris population is certainly much bigger at GEO altitudes than we currently know. Sorry, Dan. Paul.
Yeah, so what sort of discipline can be exercised on countries or agencies?
Right.
Now and in the future?
So the coordinating agency is COPUOS, the United Nations Committee for the Peaceful Uses of Outer Space. And so they meet and talk about this a lot. There's also the IADC, the Interagency Debris Coordinating Committee. And so there's no coercive measures that one can take at the moment, but people try to get rules of the road for outer space, but there was one country that really didn't want its freedom of action to be constrained in any way, and so that didn't go anywhere. But there has been evolution on this just by peer pressure. And so GEO satellites were boosted into this GEO graveyard starting in the 80s. Depletion burns for rockets to get rid of their fuel started also in the late 80s. Deorbiting satellites. 30 years ago, most satellites didn't have their own propulsion systems. Those who remember, like Einstein, and well, Chandra still doesn't, right? At least at this point, it has its own, but it can't change its orbit anymore. But most large satellites today do retain the ability to change their orbit after orbit insertion, and so can lower their orbits at the end of their missions to make their reentry either immediate or at least more rapid. CubeSats, not so much yet. Most CubeSats have been launched into low orbits from the ISS and only lasted a few months. But that's changing now with these new constellations. They're in higher sun-synchronous orbits that are going to stay up there for longer. And so there is a bit of a worry that you launch hundreds of CubeSats that are going to be up there for a long time in an area where the space debris population is already bad.
Okay, last quick question.
Yeah, sorry.
So what's the probability for occupation of the celestial?
Right, yeah. How is this going to screw up astronomers? So the covering, well, again, we can do that very easily, right? Because the mean the mean separation in low orbit, right, where most of the population is about 300 kilometers, and the typical cross section of a satellite is maybe a few square meters, and so the covering factor is let's see, 10 to the minus 4, it's like 10 to the minus 8 or something like that. So it's not a huge problem. What is a problem, of course, is the track that it leaves on your CCD. And the trouble is that you know, that space still is empty, right? But if you take a 1 minute exposure, each satellite is several hundred kilometers long. And so now your probability that you'll get a satellite track on your CCD exposure is actually very high. And I haven't done that number, but it's high, and it's going to get worse. I mean, that of course is a magnitude dependent thing, and so yeah, that would be an interesting study to do. There have also been another problem, is that the new fashionable place for astronomy satellites is the Earth-Sun L2. Which is directly in the direction of midnight, right, as seen from the Earth. And so a couple of things like WMAP have already been mistakenly discovered as asteroids, as our NPC friends can attribute. And then, you know, you see it, you've cataloged your near-Earth asteroid, and then you see it make a maneuver. And you go, no, that's not right. So, yeah.
Okay, thank you very much, John.
Thanks.